Okay, we finally have trees. Now we can stitch them together into new trees representing new sentences. This is actually a form of language modeling, which is one of the big success stories in computer science in the last few years. A statistical language model describes how likely some text would be if you just recorded what people wrote or said for a long time. For example, it might tell you what word you think would appear at the end of this. You might think sentence. And that's because you, in your mind, have a very good language model. But that's not the only thing that might appear here. Maybe end of this line or end of this utterance would all be reasonable things to put there. But end of this dog wouldn't be. If you have a statistical language model, you can sample from it, which means actually generating language. You can start with some language and generate the rest, which is what we're about to do, or you could try to generate whole sentences from scratch. I said that there's been great success in computer science in this area recently. What's happened is that modern language models really do generate text that looks like a person might have written it when you sample from them. Now, any useful language model needs to generalize from examples. So one way to get this kind of productivity is, for example, what we're about to do, which is to substitute any phrase in an utterance with any other phrase from some other utterance that has the same syntactic category, the same tag. This really simple approach isn't very good in the sense that we're going to be able to generate lots of sentences which aren't really something somebody would ever say. And that's because even though the swap that we make preserves the syntactic category, it ignores the context. Someone might say the dog ran or the water evaporated, but I don't think anyone would ever say the dog evaporated or the water ran, even though we've swapped VP for VP. Well, I said no one would ever say the dog evaporated, but then I just said the dog evaporated, so who knows. But my point is that the way in which we're constructing a language model here is very simplistic. Modern language models that work well are different in two ways. One, they aren't trained on just 36,000 sentences from a conversation with one child. They're trained from massive amounts of language. All of the text on Reddit, on Wikipedia, in fact, all of the text that can be found on the web in general. And second, the way they generate text is to represent a lot about the context using a technique called neural networks, which you could learn about in another course. Okay, but this is just an intro course, so let's do something really simple that still is like sampling from a language model, which is that we will start with the branches of the root node, flip a coin for each branch. If it comes up heads, we'll swap that branch for another phrase or word that has the same tag from some other sentence. And we'll apply this procedure to all of the branches, meaning that we'll look at all the other nodes and flip coins for their branches as well. What's the code look like? Well, we start with some tree that represents an actual sentence that was said. If it's a leaf, we're done. Otherwise, we give it new branches. For every B, we flip a coin. If that comes up heads, meaning a true value, then we come up with a new B, which is a random choice from a list of all of the constituents from other sentences with the same tag. I haven't said how to do that yet. That's something we'll solve together in a minute. But now what we do is we append B to new branches. But not B directly. Instead, we recursively call genTree, which will go through and substitute some of the branches within the branch with other things that have the right tag. Passing in our function which flips coins. Once we're done with all of that, we construct a new phrase with the same tag it had before, but a new set of branches in which some of them have been swapped out. In order to do this, we need a way to look up all of the constituents across our entire collection that have the same tag, and we'll create a dictionary of that in order to do so. So a coin is a function that generates random numbers to figure out and returns true with some predefined probability. Here's the function we just looked at, and it's going to take in a dictionary in addition to the tree that we start with and the coin flipping function. And this dictionary is going to allow us to look up the tag for the current branch to find a list of all the other branches of all the other trees that have that same tag, and then we can choose randomly among those. Here's a function that just keeps things going. We get all the trees, we build the tree index, and forever, we pick a random sentence, print it out, call the generator, which is just the genTree function, to get an edited version, and we print that out too. Input just waits for the user to press enter or return, so we're not just going to see a huge stream, instead we'll see them one at a time. In order to complete this, we need to implement index trees to create this tree index, where we're building a dictionary that we're going to return by going for all the trees in trees. Then we need to go through every tag node pair, where the tag is the tag for the node, and we add that to our dictionary. If we've never seen this tag before, then we make a new list. Otherwise, we can append the result to the existing one. And how do we get all of the tag node pairs within a tree? Well, let's traverse the tree and append them all to the result. What does it mean to traverse a tree? It means to append the tag and node itself to the result list, and for all the branches, do the same thing. Traverse the branch. Then we traverse the whole tree and return the result. Finally, we call the generate function to do the work, and we'll see what we get. So I run the program, I get the original, okay, which one do you like best of the ones that are left? And then we run our process of calling genTree, and we get no. Which dog look for a school when you to build that someone when her think changing your diaper? What happened? Let's go ahead and print some things out. So during genTree, we had some original, and then we made a swap, and we swapped the original for, and let's take a look at what we were dealing with in the first place. Okay, which one of you did you like best of the ones that are left, which had this structure? We swapped the OK for the no, which were both interjections. We swapped which for which, one for dog. Then we made a huge change. We swapped do you like best of the ones here for something completely different. Look at this book before you go to bed. Then we recursively started swapping stuff in here. At became for, this book became a nap, nap became school, etc., 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 and we ended up with know which dog look for a school when you to build that someone when her think changing your diaper. So taking away the extra printing, let's look for one more, and then we'll call it a day. Oh, I'd love to see a puzzle with animals on it. Oh, I'd love to give something will go the money of, I would give you the spaghetti for your shelf too, if it is see over, etc., etc. Oh, you're going to make them go around in a zoo. Oh, we're going to make them go tonight in a zoo. This isn't a great language model, but it's not totally generating gibberish. It's making some reasonable substitutions. It's just that if it makes too many of them, then things tend to spiral out of control.